So welcome everyone to the astronomy seminar, to the astronomy department, and to special guests from Astronomy 401, who, by the way, were here before everyone else was here. So if that motivation scales in that sense, right? So we know who the true fans of this are. Okay, so it's a pleasure to welcome Diana Dragomir today. Diana got her undergraduate and master's degree from McGill University. If you don't know where that is, it's in Montreal in Canada. So she worked on various projects on exoplanets there. Then she moved to the University of British Columbia, and then from there went to Santa Barbara, and now is a Hubble Fellow and Copley Institute Fellow at MIT. I think there was a stopover in Chicago somewhere between.
I'm only one fellow.
So you're only one fellow, okay. Well,
just the whole.
Well, this is a pretty good fellow to be, so if you don't know anything about this, this is a prestigious award in astronomy that's given out. So she's one of the world's experts on atmospheres and exoplanets, and she's going to be talking to us about super Earths today and what they are and how to find them and understand them.
Okay, hi everyone. Thank you for inviting me. It's great to be here. It's actually my first time in Texas. That's not just like Houston Airport, so it's kind of cool. Now I know that maybe you're all a little bit distracted, so you might have other things on your mind than super Earth right now, given what's going on this week. So let me just say, whatever happens tomorrow, if you don't like it, you can always just come to Canada. So got lots of space, a little bit of snow, but it's very pretty. So
Where is that picture?
that's actually in Alberta. It's Lake Moraine. Yeah, I took that. I think Russ showed that picture too. It's going all over. All right, so I'm going to focus on the super Earth exoplanets, but let me just give you a quick overview of exoplanets in general, really quick, because there's actually a lot to say just about super Earth. And I'll get to the definition of what I mean by a super Earth in a moment, but that's after the intro. So let's have a look at this. This is the first time I'm showing this plot. And I realize it's actually important to show it more often because it basically shows you the number of exoplanet discoveries as a function of time. So let's ignore this point for now. Maybe you can ask me about it later. But from 1995 on, this is basically when the first exoplanet around a main sequence star was discovered. Okay, so like not around a pulsar, but just like a regular. It was like I want to say G-type star, kind of like our sun. 51 Pegasus E. And from then on, planets have been discovered at pretty much exponential rate. And you can see, as a function of color, the methods that were used. And I'll go over some of those soon in a couple of slides. But basically, radial velocity was the main way to find planets early on. And that's basically, well, why don't I just review it afterwards? And then the transit technique ramped up real fast from the early 2000s on into this year, basically. So, and the reason that the number of planets here is low is because the mission that discovered all of these planets here, Kepler, if you've heard about it, its goal was to actually discover a lot of transiting exoplanets. While all the exoplanets found by that mission were eventually confirmed and announced, in this year. I think that was like 2013, 2014. And then that mission is now doing something a little bit different and is finding fewer planets, and that's why this is still going up. We'll need another mission that's going to be as big as Kepler to keep going up. But I think we have quite a few planets to work with at the moment, so I'm not too concerned. This is getting a little old, but the important thing here is that we have like 3,400 confirmed exoplanets. Okay, that's a lot. It's a lot. It's a lot of planets that you can do all kinds of stuff with. But actually, turns out, as you'll see, that it's not that easy to study the vast majority of these planets. We're pretty limited by a lot of things. And we also know about 5,000 exoplanet candidates. There just aren't enough telescope resources to confirm all of these planets. I won't go over why they need to be confirmed. But let's just say that it's pretty hard to find a planet. You can't just use one method, get a signal, and be like, okay, that's a planet. Okay, so you have to vet it because there's often other astrophysical events that can cause the same thing. So we've got orbits, orbital periods. For example, the Earth goes around the sun in 365 days. We've got orbital periods for exoplanets, currently from about 8 hours, which is really, really crazy, okay, because that's a really hot planet, to about 17,000 days. It's actually really hard to measure really long periods, because you have to, 17,000 days, I'm not sure how many years that is, but it's probably of the order of how long we've been observing exoplanets, okay? So if you want to find a planet, an exoplanet that has a period of 30 years, and be sure that that period really is 30 years, you have to observe it for at least that long, so you can see the signal repeat itself. So that's why we're limited. But there may be exoplanets with longer periods than that. Planet 9, if it's real, that's probably a longer period than that. And orbital eccentricities, that's basically how elliptical the orbit is. Most of the planets in the solar system are in circular orbits, but we've been finding planets in other systems, not the majority of them, but quite a few that have very elliptical orbits. Okay, so I won't talk about those too much either. You'll have to invite more exoplanet people if you want to hear about these things. And we can currently measure masses as low as 1.3 Earth masses, but we're pretty sure that there are planets out there that have Earth, like masses of the order of 1 Earth mass or smaller. It's just that our technology right now is limiting us to about 1.3 Earth masses. And we have discovered planets, transiting planets in this case, with sizes, radii, okay, as small as half a Earth size. And again, we're limited by precision with which we can make these measurements. There are probably planets out there that are smaller than that. Okay, so the radial velocity method. This is important because it gives us one important piece of information about the planet. Several actually, but one that we care about, especially for this talk, and that's the mass. So the way this works is you look at a star, you point a telescope that has a spectra at a star, and you monitor it for some time, and you hope that you'll eventually observe the spectral lines of the star shift around the central wavelength. Okay, as a function of time. And if they do that, that's great. It's usually a very, very small shift. It means that there's another object in orbit around that star. Okay, and depending on how much the lines shift from the central wavelength as a function of time, that tells you how massive the other object around the star, or the object around the star is. Okay, so in this case, what happens is that when the star is moving away from us, it means the planet is moving toward us. But when something moves away from us, the light from it is redshifted, and when the planet is sort of on the other side of the star, and the star is moving towards us, then we get blue shifted light. So we can measure really, really tiny signals like that and get masses for these exoplanets. This is the signal for the first exoplanet ever found. The radial velocity is a measurement that we get from that shift in wavelength. Okay, so it's the speed at which not the planet but the star moves. So this is the velocity at which the star moves, and we can detect that the planet moves at 50 meters per second because of the planet in orbit. Sorry, did I say? We can detect that the star moves at 50 meters per second because of the planet that is in orbit around it, causing it to wobble. So that's pretty crazy. Now we can go down to like 2 meters per second these days. Okay, 2 meters per second. So feet? Do you need feet? I can do feet. 6 feet per second, okay? That's the velocity of the star back and forth. That's a function of time that we can actually measure. These stars are really far away. Okay, so we get the mass from that signal. And then we have the transit method. This is a video. Okay, it started. Basically, if your system with a star and a planet is aligned just right relative to your line of sight, then you might see, well, you probably will see the planet pass in front of the star as it goes around the star in its orbit. So that doesn't happen very often because you really need the right orientation, but luckily there are lots of stars in the galaxy. So if we look at enough of them, once in a while we should see a transit signal. And we see a lot of transit signals. There are a lot of, most exoplanets at this point have been discovered this way. And the transit signal tells you another important quantity about the planet. So we have the mass, and now we can get the radius from the depth of this signal. So as the planet goes in front of the star, it blocks out a little bit of the light from the star, and you see that in the luminosity of the star as a function of time, the brightness of the star. And you see that there's a little dip as the planet goes in front of the star, and by measuring the depth of that dip, you get the size of the planet. Okay? Now, soon we'll have really big telescopes and we'll be able to do really cool things. So you can get a transit for an exoplanet But then we'll be able to measure with really high precision whether or not the planet is habitable, okay? And if it's inhabited, that might be another 20 years or so, but that's what we expect the transits to look like. So, yeah, not really, okay? All right, let's get into atmospheres. So, exoplanet atmospheres. The important thing, these are really important. I'm going to spend a few slides describing this because it's going to set the pace for, or the background for the rest of the talk. So when you have a planet that transits a star, right? Then here's an example of the planet transiting. Here they call it primary eclipse, but we'll just call it transit. You can actually observe its atmosphere. You can see the light from the star going through the atmosphere of the planet and getting to you, okay, to Earth. And that way you can actually probe what's inside the atmosphere of that planet. The other thing you can do is when the planet goes just behind the star, you can get like the really bright, so the day side of the planet, you can get the bright side of the planet, and get an emission spectrum from that. So it's going to emit some light at different wavelengths, and you can get a spectrum from that as well. So another way of looking at it, transmission spectroscopy, which is going to be the main focus of this talk, but I'll talk a little bit about emission spectroscopy as well. Here's another way of looking at it. You've got the starlight, and anything that goes through the little thin layer of atmosphere is filtered and imprints the composition of the atmosphere onto the starlight, and you get that, you measure that at Earth, and you can figure out what the atmosphere is made of. Here's another way of looking at it. This is important because I'm going to get into clouds, actually. So here's what happens in the best case scenario. You've got this, particles of atmosphere, the starlight goes through, and when it comes out, it has imprinted on it the signature of the planet's atmosphere. If your planet atmosphere is not puffy, okay, if it's really shallow, like the Earth is, for example, then you won't get as much of a signal, because most of the star rays will not go through the atmosphere. So basically what that means is you get less of a signal. And the other thing that can happen is if you have clouds at the top of the atmosphere, then that keeps the starlight from going through, so instead it just kind of reflects off. And then you again don't really get to see what's inside the atmosphere of the planet. I'm going to go over this very quickly, but basically this is how we measure. The scale height is just a measure of how puffy the atmosphere is, okay? And it comes from the ideal gas equation, more or less. But the scale height is something to keep in mind because I'm going to use this word throughout the rest of the talk. So how do we do spectroscopy of exoplanet atmospheres? Okay, well, we look at a planet during transit, so you have to look at it at the right time, and you look at it at the transit as a function of wavelength. So here is an example of that, basically from 1.1 to about 1.6 micron in wavelength. They just basically measured the transit depth at each of these small wavelength bins. And then you can plot that up on a graph like this. So here on the vertical axis, we have basically the depth of this transit as a function of wavelength. So going down this way, it goes to the right this way. So in this case, this is a zoom of the region the wavelength range that's actually probed by this particular instrument. You end up with not very much variability in the transit depth as a function of wavelength. So this was actually done for a really exciting super Earth called LISA 1214b. Unfortunately, in this case, what it probably means that, the fact that you don't see anything in the spectrum, and I'll get back to what you expect to see in a second, the fact that it looks flat tells you probably there are clouds in the atmosphere. So that's a bit surprising, and it's also kind of bad news for hoping to do this kind of work for planets in the future, because if there are clouds, you just don't have access to what's inside the atmosphere. The light just doesn't go through. So here we're looking, I remember I talked about scale height. The green line, which is, well actually, the green line here is different than the yellow line here, but let's look at the yellow line here. So this is, in this wavelength range, these are water molecular absorption bands. So if you have a really puffy atmosphere, you expect to see, and no clouds, you expect to see a signal that's about the size of the yellow line here. And that's not because there's a lot of water in the atmosphere, because I did say these are water bands, but because that water may not be very abundant, but it's spread through so much of the atmosphere because the atmosphere is really puffy, that you get a lot of starlight going through, And so you basically just have more signal that way. Does that make sense? Okay, so you get a larger signal because you have a puffier atmosphere. So that doesn't tell you that there's water in the atmosphere. It tells you there's a bit of water, probably, because that's the wavelength you're looking at. But what it really tells you is that for the atmosphere to be that puffy, it has to be hydrogen or helium dominated. So in this case, if they had seen a signal that large, it would mean that the atmosphere is hydrogen or helium dominated, because that's like the lightest element that you could form an atmosphere with such a large scale height. Okay? In this case, unfortunately, it was flat. And they thought, okay, well, maybe it's just a shallower atmosphere. So then you would have seen this blue line. See, so if you only had water and no hydrogen, the atmosphere is smaller, and you would only see this blue line here, and which is a lot smaller than the yellow light up here. You can see the blue line here. But it would still tell you that, okay, well, it's a small atmosphere full of water. They don't see that either. So they're down to a level where, you know, it's not any of the usual things that we would think would be the atmosphere of this planet. So either it has no atmosphere, which cannot really be true in this case, because we know the density of the planet from the mass and the radius. And we know that it's a really low density planet. And rock has a higher density than that. So this planet cannot really just be rocky with no atmosphere. Okay? So then the conclusion is, well, we don't see any spectral features. It must have an atmosphere. It's probably covered by clouds. Okay? There is a problem with transmission spectroscopy. Actually, there are many problems. This is an important one to keep in mind, and I recently just learned about this. So if you have a really large feature, like the light blue feature here, that tells you that you have like a really puffy, hydrogen-rich atmosphere with no clouds. If you have clouds, what clouds do, they'll give you something like this orange line here. So you can imagine that basically the cloud is really high up in the atmosphere, and what it's doing, it's cutting off the atmospheric, the molecular absorption above a certain level. So you'll see anything hydrogen or water-rich that's above the cloud, if you're lucky, if there is anything. So it'll just look like less water because you're only seeing a little bit of atmosphere at the top of the cloud. But you won't see anything below the cloud. So you get this orange line here. Now, if you have a shallow atmosphere, okay, then you would get the same thing as the blue line, but smaller, because your atmosphere is smaller. But you could have something else that would cause the same signal. And that something else is a partial cloud. So here's how I would explain this. If you can either have a shallow atmosphere, and that's why you don't see a lot of signal, or you can have half or part of your atmosphere covered by cloud, and you're only seeing light through the other half of the atmosphere. That's also going to give you a shallow signal. And it turns out those two are indistinguishable. This is kind of really bad news because a lot of planets right now seem to have atmospheres in this regime. It's really bad news for figuring out whether the atmosphere is just really small or whether the atmosphere is actually really large, but it's got like a little bit of cloud in some parts of it. So it's a degeneracy that's really hard to break. So what can you do instead? Well, you could try emission spectroscopy. So remember when I said the planet can go behind a star, so you can get you can see the light emitted from the bright side of the planet. And then I won't get into this because this is anyways for a hot Jupiter planet, not for a small planet. But this allows you actually to be less sensitive to clouds because now you're not looking just through the ring, the outside ring of the atmosphere of the planet. You're actually looking directly through the atmosphere, perhaps much deeper into the atmosphere of the planet. So even if there's clouds, on some of that surface, you should be able to get some signature from around them. Okay? And you can see through clouds a little bit deeper as well. So if the clouds aren't very thick, you might be able to see below. So emission spectroscopy is really good. The real problem here is that you need a hot planet for this to work. So if your planet is not hot enough, which means it's not close enough to its star, for example, then you won't get a very strong signal. You need light, you need photons to make this work, and if your planet is too far from the star, it just doesn't emit enough photons and you don't get enough signal to noise to do emission spectroscopy. Whereas transmission spectroscopy works as long as the planet transits, it doesn't matter how far it is from the star. Quick review of phase curves. I'll get into supers soon, but this is important. You'll see why. So the other thing we can do is get a phase curve. So now we're not doing spectroscopy anymore. This is really just the luminosity of the system, the brightness of the system as a function of time. So here's a zoom out of the of an example. So as the planet goes around its star, you see more and more and more of its daylit side. And that looks like a transit here. And then an increase in brightness. And then the planet goes behind the star. So you get a little dip in luminosity because it's gone. You only see the light from the star now. Then it comes out again, so the star gets bright again. And then it goes down again and gets to transit. So here's a zoom in. The transit is somewhere like all the way down here, so you don't see it, but you see the secondary eclipse. And you see that as you go through the orbit, you get fainter and then you get brighter again. Then the planet disappears behind the star, and then you go back to where you started, come back around, it gets fainter again, from bright to faint, and then transit, okay? So from this you can learn a few things. First of all, from the eclipse depth, you can learn how hot the planet is, okay? So you know how much, here you see the planet and behind the star you don't. So how much heat has disappeared from the system when the planet goes behind? That's the amount of heat that you expect from the planet, and that gives you the temperature of the planet. And these phase curves give you the amount of, how well the planet redistributes heat around itself. Okay, so in a case like this, it probably doesn't redistribute heat very well. But you can imagine that if the planet has circulation in the atmosphere that circulates the heat from the day side to the night side, you might actually get a similar temperature on the day side and on the night side, and this might end up being pretty flat. So you'll get a transit, and then like a flat line, and then an eclipse. Most of the time, that's not what we see. We see a phase curve. But there are cases when this is almost flat. So these are our main tools right now for learning about exoplanet atmospheres, these phase curves and emission and transmission spectroscopy. So let's review what these can do. So transmission spectroscopy tells you how puffy the atmosphere is. It can tell you if you don't have any clouds. It can tell you what kind of molecules, what the atmosphere is composed of. Meanwhile, emission spectroscopy will tell you the temperature of the planet. It can give you the emission spectrum. So you can get something about the atmospheric composition as well, and it can tell you how well the heat is distributed around the planet. All right, super Earth. So I'm just going to define super Earth for the purposes of this talk as any planet with a radius between 1 and 4 Earth radii. This is my baby. This is what I'm really interested in. And the reason for that will become apparent in a minute. But basically, gas giant planets larger than Neptune, we're pretty sure, they're not rocky, right? So they're all going to be Jupiter-sized. They're going to be gaseous planets. Can't have life on them. But also, importantly, they're going to be gaseous planets. We don't necessarily know what they're made of, but generally it's going to be a mix of hydrogen and helium. In other words, you can generalize more about gaseous planets than you can about small planets. Now, with small planets, and I'm just going to say super Earth from now on to avoid confusion, smaller than about 4 Earth radii. Well, the most important part about them is that they're actually really frequent. So this is basically number of planets discovered so far as a function of size of planet. So you can see that at large sizes, so Jupiter is around here, and then Neptune is around here. So at large sizes, there aren't that many planets actually. There aren't that many gas giants that we're discovering. Most of the planets in the galaxy are small planets. They're super Earth. They're smaller than about 4 Earth radii. They may even be, even Earth-like planets seem to be fairly frequent, but those are actually, now we're getting into a different problem because it's just really hard to detect. So we don't really know very much about Earth-like planets or sub-Earth-sized planets because we can't find them yet. Earth is hard enough. So really, the best we can do right now is kind of the super Earth region. So they're very numerous, they're everywhere, but we don't have any in the solar system. And unless Planet 9 turns out to be real. But we may never actually be able to see it. So we don't have any super Earths in the solar system. We have Earth and Venus, which are about the same size. Mars and Mercury are smaller, and then you jump straight up to Neptune, and there's nothing in between in size. There's no 2 or 3 Earth radius planet in the solar system. But they're everywhere else around all the other stars. That's intriguing enough for me. Not necessarily because of habitability or anything like that, although who knows, maybe we don't know anything about them. They could be habitable in some cases.
So is the big deal about this figure that it's consistent with being flat below, but it's not consistent with rising?
Given the error bars, it's hard to say.
But the point is it's not consistent with like a continually going up, right?
No, but I would not put my hand in the fire that like these error bars are not underestimated a little bit.
Okay.
But yeah, I would say it kind of plateaus. Other papers have found the same thing. Like it gets pretty constant at less than for 3 radii. Yeah, forget the thing I said before. That's just because I want to see more data. But
this is basically all Kepler, right?
yeah, this is all Kepler. Yeah. So you think now we have a great sample of super Earths that we can study, but that's not true. And the reason it's not true is because the host stars of these planets, of all the Kepler planets, are really, really faint. Now that's by definition because the Kepler mission was trying to find as many planets as possible. So in order to do that, you want to stare at one part of the sky for a long time, and you want to pick a part of the sky with lots of stars. If you want to have lots of stars that are not mixing over each other, then you want to go pretty faint, right? If you're looking anywhere where there's too many bright stars, you'll never have very many bright stars in one field of view. But basically, they try to avoid bright stars. Just looked at faint stars. You also don't want to saturate your detector with bright stars. So if you want to find lots of planets, you need to do a survey of faint stars. Is what I'm trying to say. But then you can follow up. It's really difficult because of the lack of photons. Other instruments aren't as sensitive, so you can't get additional information on these planets. You can get statistics though. And that's what we found here. Another reason super Earths are interesting is because they can have a variety of compositions. So you could have, models show that you could actually have like a 3-Earth-sized radius planet that's rocky, terrestrial, like Earth. But the same models also say that depending on how it formed initially, it could also just be a mini gas giant like Neptune. So there's a lot of degeneracy in this radius range between 1 and 4 Earth radii, where we really don't know if these are rocky planets, which would be important to know for habitability, or whether they're actually just small gas giants. And where is that threshold, right? At what size do planets kind of generally become gaseous? And below that size, they would be rocky. We're starting to get an idea of where that threshold is, but we don't understand it very well yet. So this is just a little diagram of something we call the ice line. It's basically the distance from a star beyond which water condenses into ice, or freezes basically. So the general idea until very recently, and some people are still trying to push this actually, is that if you find a planet that has a lot of water in its atmosphere, well, at least we can say something about its formation. And that something would be that, well, it formed out here beyond the ice line. Why? Because in order for it to have a lot of water, it needs to have accreted pieces of ice. And then over time, it may have migrated in close to the star where we see it today. If it formed closer to the star, all that water would be evaporated. It would actually be pretty hard. It's there in vapor form, but actually some of it might be dissociated with hydrogen and oxygen, and you won't accrete it the same way. You're not actually going to be able to accrete that much water when it's in gaseous form. So if you have a water-rich planet, we think it must have formed out there. But that's mostly true, but you could also imagine a scenario where you have small planetesimals that migrated in from the ice line, migrated in and assembled the planet closer to the star at that point, before they had a chance to evaporate. So it's actually very difficult to relate atmospheres and planet composition to where the planet formed and came from. And this is just to I'm putting all the depressing stuff first so that you can better appreciate how difficult this is. There are a lot of degeneracies, but it's still a very important tool. Mass and radius don't tell us everything. So what we really need is a lot of planets, a lot of small planets that we can observe with the telescopes that we have and that are coming up. But not just any small planet, because as we saw at Kepler, because of the faintness of the host stars, we can't really follow up those planets with other instrumentation. So one way to get planets with a good signal to noise is to look for planets that transit small stars, because the contrast of a small planet and a small star is just going to make the transit look deeper. Or you can just go for bright stars, which is almost a little bit the opposite. You'll go for earlier type stars. If you have enough photons, so here, for example, you're looking at a 1.5% transit depth. And here you're looking at a 0.1% transit depth. they're taken with very different telescopes, so they're hard to compare just in terms of signal to noise. But you wouldn't be able to see a 0.1% transit depth here. But that's okay, because this gives you about a 2 Earth radius planet, and this gives you about a 2 Earth radius planet. So you could go either way. I'll just skip over this one, actually. Apparently it's an update too. So we don't have very many planets right now that have either one of those characteristics, small planets, okay, for which we can do atmospheric characterization. So here they are. This is a little bit out of date. There's probably a couple more in here. But basically what we're looking at here is the signal to noise of the transit. So how well you can distinguish the transit as a function of planet radius. So these are all the hot Jupiters here. They have, you know, the ones with really good signal to noise have actually already been observed. We're starting to learn more about them. But in terms of the smaller planets, this area of parameter space is still pretty small. So a small planet that has a good signal to noise ratio, either because its star is small or because its star is bright, there aren't that many. Here they are. And I'll talk about what we're doing for precisely these planets in a moment. But maybe just further motivate that with the very famous, if you should know about this, the mass radius diagram for small planets, okay? So remember I said we can get the masses and radii for planets under certain circumstances. So if the planet transits a bright star, well, if the planet transits, first of all, we can get the radius. And if the star is bright enough to do radial velocity measurements, we can get the mass. So here are the planets for which we have these two quantities so far. I'm limiting it at 20 Earth masses and 4 Earth radii because I'm really interested in the super Earth. And these are density curves for just idealized compositions. So depending on where a point falls in here, it's going to tell you roughly what composition you expect for that planet. So in case you can't read them very well, this is just kind of a basically iron core only planet, Earth-like planet, pure rock. The reason that pure rock is a little less dense than Earth-like is because pure rock just assumes there's no iron core. We don't really know if that's feasible or not, but we gotta start somewhere. So these are just idealized compositions. A pure water planet and then a hydrogen planet. You can see that the planets, small planets we know so far, are basically all over the place. And importantly, their uncertainties, these are the error bars, especially in the mass, are such that in this regime here, it's very hard to say just from the mass because we don't understand it well enough yet. We can't measure it well enough, whether it's a water planet or a rock planet. And in between here, you can have a variety of compositions. Like you could have something with a small iron core and a lot of ocean, or you could have something with a large iron core and a lot of mantle, for example, and a little bit of hydrogen on top. And those potentially produce the same mass and radius, but it's very different compositions. So again, we're getting down to measuring the density is great, but it's not enough to get a detailed composition of the planet. So what we have so far for transmission spectroscopy of small planets, GLISA 1214, I showed you this earlier. We get a flat spectrum, and we think it's due to clouds. Then there's GLISA 436. This is a slightly larger planet, a little bit hotter than 1214b. It also shows a pretty flat spectrum, so we think that it's either a very, very small atmosphere, but again, we know that this planet has a low density, so it must have a large atmosphere. Or clouds. So clouds are probably more likely in this case. With less precision, we're starting to see this for super Earth as well, 97658b. We're getting some systematic noise in the spectrum here. These are all Hubble Space Telescope spectra, by the way. It's basically the state of the art right now for probing this wavelength range where we're looking for this water signature, and we just want to see if it's there and we want to see how big it is for starters, and we can't even do that yet. So, that's the depressing stuff, like I said, but we're getting there. I do have some positive stuff, I promise. Okay. And then TRAPPIST 1 and 2, 1B and C, which you may have heard about. These are Earth-sized planets transiting a very, very cool star. So the star is very faint, but because the star is very small, you can actually measure the transit really well. And these are pretty, habitable zone planets, so they're very interesting. But with the precision that they were able to get, right now they also get a bit of a flat spectrum. But in this case, the precision is not good enough to exclude other models. It's not necessarily saying it is clouds. They haven't gotten the error bar small enough to say that. All they can say here is that it's not the red model, which is a puffy hydrogen atmosphere. Kind of expected for such a small planet. You wouldn't expect to see that anyway. But they wanted to check, so it's good that this was done. Okay, so there is a case where we have measured a little bit of a signal. Hopefully you're starting to get familiar with this bump here in this wavelength range, the water feature. So for HALP 11, which is, again, like a Neptune-sized planet, kind of hot, warm. You might consider this really hot, but we actually know a planet is much hotter than this. So consider I consider 1000 Kelvin about warm, and below 700 Kelvin is actually cool. But it's still not that cool. It's, you wouldn't want to go vacation there. So here's the signal that they got. This was an Nature paper from a couple of years ago. And it's pretty exciting. It's basically saying that it's not cloudy because you're not seeing flat and then you're seeing a bump and then flat. You're actually seeing the full molecular feature of the water band, but it's really compressed. So that's just saying that the atmosphere is a lot less puffy than we thought for this planet. That's still consistent with its fairly low density, so that's fine. But remember what I said about how partial cloudiness can also cause this. So this could be a very puffy atmosphere, but partially cloudy, and you would get the same signal. And in this case, they conclude it's actually just a not very puffy atmosphere with no cloud. But that's before the other paper came out. So I don't know. We have to keep thinking about this. So remember those 5 planets I mentioned earlier? We are looking at those planets with the Hubble Space Telescope and the Spitzer Space Telescope. They're the only ones we have right now that are bright enough, that are suitable for characterization. So there are some large programs that I'm involved with, all of them in some fashion, to get transmission spectroscopy for all these planets. So even if they all have clouds, at least we can say something statistical, a little more statistical about these planets. And that has implications, right? Because when the James Webb Telescope will be launched, if we can determine that some of them don't have clouds, maybe we can start figuring out, well, can we tell ahead of time which planets are likely to have clouds and which not? And then maybe don't spend too much James Webb time on the ones that have clouds, because all you're going to get is a flat line with better and better precision, which is not all that useful. So we have a lot of time on this. Most of the data was taken and we're looking at the results. For many reasons, some of these data sets are really hard to deal with, but if you want to know more about that, we'll talk about it later. Here are some preliminary results. So we are back to some signals in some of the small planets. This is 3470, one of my favorite exoplanets. And here you can see what I said earlier about have this cutoff here, right? So you don't actually see the full, it's hard to see here, but there's a yellow line here that is same as the yellow line here. And that would be like puffy atmosphere with no clouds. And we don't see that, but we do see a little bit of a signal. Cut off here, and then it goes up and down again, and some weird stuff is happening here. So what this is saying is, well, there are clouds here, but we're actually able to see a little bit of the atmosphere that's above the clouds. Luckily, the clouds aren't so high. We still managed to probe a little bit of the atmosphere above the clouds, and we can, that helps us kind of say that this is definitely a puffy planet. It's cloudy. It's got water. It's probably hydrogen. Its atmosphere is hydrogen dominated. Another thing you can do when you have clouds, this is the same planet, is instead of looking, all of what I've showed you so far has been in the infrared, but you can also look in the optical. And if you look in the optical, you can see things like the slope here that you see a lot of the models. It doesn't really matter what they are for what I want to show you, but basically a lot of composition models will show you that there's a slope, so the radius of the planet will increase towards smaller wavelengths. The planet will appear bigger, and that's because of Rayleigh scattering. So it's not really absorbing more light at those wavelengths, it's just scattering the light at those wavelengths. So you don't see, so it's effectively the same as the atmosphere not being as transparent as down here. So here the planet appears smaller in many models because the light goes right through and your transit just appears shallower. But then here it can appear larger. So what we've seen in this case is that most of these models predict a little bit of Rayleigh scattering, but we actually see a pretty large Rayleigh scattering signature, which is telling us, it's pretty much consistent with what I showed you on the previous slide. It's telling us that there are clouds and hazes that are scattering in addition to just Rayleigh scattering from the hydrogen, and it's causing this really steep slope here towards the blue. So even though these error bars are pretty big, I show all the points for consistency. The ones that have really large error bars don't affect the analysis very much. But the important take-home message here, even though we can't see the slope in a lot of detail, is that the points at short wavelengths, shorter than 0.5 micron, 3 different instruments at different times, all show deeper transits. So the planet really does appear to be larger in the blue, which says that there's definitely a lot of scattering going on in the atmosphere. This is also really cool because even though this has been measured for hot Jupiters, this is the smallest planet from which we have Rayleigh scattering. So there's hope, there's complementary observations you can do whenever you may end up with a flat spectrum in the infrared. The other thing you can do is try emission spectroscopy. So, like I said, this is better for probing through clouds, but you need a really hot planet. So you can't just do it with any planet. So here comes 55 Cancri. This is like my most favorite planet, but I spent so much time on it, it's about to become one of my least favorite planets. Don't tell it that. It's not going to be happy. Okay. So let's just bring this up. Oh, it's reverse order anyway, that's fine. Okay. So this is the ID file of the planet. It's a 1.9 Earth radius, 8 Earth mass planet, which puts it right around here. This orange line, to remind you, is the pure rock line. These are the latest measurements. They may change again because this is a very small transit and it's very difficult to measure signals precision at that level. But it's going to be around this, around 2 Earth radii, which puts it just a bit above the rocky line. So the latest papers are saying that it's consistent with being a rocky planet, but it still seems to, because we don't think there are such things as just pure rock planets. They usually have an iron core. So a rocky planet would be like closer to Earth, like here. So we do think that this has some type of atmosphere. Its density suggests it has some envelope on top that's making its radius a little too large for its mass, for it to just be a rocky planet. And it's orbiting a pretty large star, almost like our sun. And luckily, it's a very bright star, so we actually get a really good signal, but the signal is very shallow. This is 300 parts per million. You guys want me to use like millimagnitudes or parts per million? A lot of the plots I showed you were parts per million. That's more impressive, right? So the transit of this is 300 parts per million. You'll see it in a moment. And the star is really bright, so that's great. Lots of photons. There is something a little bit wrong with this planet, and it has to do with this whole rocky controversy. From Kepler, we also learned that for planets that have orbital periods less than 1 day, just like 55 Cancri has an orbital period of 18 hours, it's really hot, it's really close to its star. For those planets, there aren't any that have radii larger than about 1.6, 1.7 Earth radii. There's also a paper by Leslie Rogers, who's an expert on modeling the interiors of these planets, which found, based on observations so far, that it seems that in general, so this is a statistical argument, in general planets larger than 1.6 Earth radii will have an atmosphere, and the ones smaller than 1.6 Earth radii will be rocky. There can be exceptions, but in general that seems to be true. So look at this. For the really close-in planets, Kepler doesn't find a lot of larger planets larger than 1.7 Earth radii. Now this only goes to 4 Earth radii. So, there are hot Jupiters, there are gas giants at really close periods. But in the small super-Earth regime planets, you don't get much bigger than 1.7. So that's kind of saying that those really hot planets are probably rocky, which kind of makes sense because they spend so much time really close to the star, and they have a lower mass than a gas giant, so their atmosphere would have evaporated long ago. They don't have enough mass to hold on to it, and at that kind of crazy temperature, they would have lost their atmosphere. So this makes sense physically, intuitively. 55 Cancri is around here. it wasn't discovered by Kepler. So, it's a little bit larger than we expect for a planet that close in. So that's, it's strange. It shouldn't have an atmosphere, but it might. So it might be our only shot to do emission spectroscopy of a small planet, because it's hot and it might have an atmosphere. Most of the other small planets that are hot don't seem to have an atmosphere, which makes it hard to do emission spectroscopy. Okay, this is a really cool result that came out this year, actually. So there's a lot to see in this phase curve. Let's go one by one. So this is for 55 Canton E. This is a transit. Remember I said it's about 350 parts per million? It's a really shallow transit. But they still get a really good precision. And that's where you get the size of the planet from. This is the eclipse here. So this is when the planet goes behind a star. You get the temperature from this. And from this depth, they measure that this planet is really, really hot, 2400 Kelvin. It actually turns out that that's hotter than you can explain just from the heating from the star. So it's really weird. Just from the stellar heating, it should be about 2100 Kelvin. So with the error bars, you could still make it work. But this planet is crazy. Like, it's hotter than we even expect it to be from being so close to the star. And then the last thing is this offset here. So remember how the phase curve gets, the phase curve of the planet gets brighter as the planet goes closer to going behind a star? Well, normally you would expect the eclipse to happen at the peak of that light curve. So it gets really, really, really bright, then it disappears behind a star, and it comes out again, and it's still bright, and it faints. It gets fainter as it comes towards transit. But in this case, it's actually offset a little bit. So what that says is that the hottest part of the planet is actually not the part that's facing the star. Just think about that for a minute. It means that the hottest part of the planet is a little bit, I think well, it depends how you define east and west on these planets, but it's not the part that's facing the star, it's the part that's a little bit shifted. And what that says is that you need, well, I think that it says that you need to have some sort of atmosphere that's going to transport the heat a little bit around the planet. And then the other weird thing is the fact that the eclipse depth is deeper than the level of the transit depth here. Think about this if you want, but you can just take my word for it too. This means that the planet actually emits a bit of heat on the night side too. So if the planet was completely cool, like 50 Kelvin or something on the night side, then the level of the bottom of this eclipse would line up with the top of the transit. But because it goes below that, it's saying that the night side of the planet is a little cool too. It's a little warm as well, yeah.
What's on the error bars on the temperature?
I think it's about 150. Yeah. Yes.
When you say that there's an offset between where the peak temperature is and what's facing the star, does that mean that there's like a lag between it and it's spinning, or is it like tightly locked?
Yeah, so I don't know if I made that clear enough. Most of these planets are really close into the stars that close enough that they're probably all tidally locked. So if you have any offset like that, I guess what I'm trying to get at is this paper claims that this is a rocky planet and potentially a lava planet, and that's why it's so hot. But I'm saying, and not just me, but I'm saying, well, because there is an offset and the eclipse is not centered where the peak of the phase curve is, that suggests that there is some recirculation of the heat. That can happen even if the planet is tidally locked. If you have an atmosphere, you can have winds, but just the bulk of the planet will be locked. You can have winds and currents that will just kind of shift the heat. But having spoken with geophysicists, they don't think that you can have lava transport the heat that much to one side. Maybe you can with lava, but you cannot explain the nighttime temperature, which is about 1300 Kelvin, if I remember correctly, with that. Because as soon as you would get to sort of like the sunset part of the planet, the terminator, where you were about to enter the night side, it would cool really fast. Lava just doesn't have enough flow to transport energy all the way to the night side. So if it was a rocky planet, you expect the night side to be really cold, but they measure 1300 Kelvin. So all these things are arguments for saying that, well, there's probably some type of atmosphere on this planet. Why is it so hot? Well, you could have systematic noise in the light curve, but we have to take these face value. So there's the night side temperature, yeah, 1400 Kelvin. This also has an uncertainty of like a couple hundred, 200-300 Kelvin maybe, yeah. But still, it's not 50. It's not really low. So I thought what we really need is more data for this planet. Maybe at some point we'll give up, but I hope that we'll figure something out before we have to. So I use HST and Spitzer, and that's because those can probe different infrared wavelengths. So I really wanted to look at as many wavelengths as are accessible to us. What I showed you in the previous slide, that was a Spitzer light curve, so 4.5 micron. So we got basically 4 eclipses to observe with HST, and then 4 in each of the 2 wavelengths that Spitzer can observe right now. Just as before, so that we can really build up the signal to noise, and also as a cross check, right? You hope they find the same thing in each eclipse. And then this is the brightest star that's been observed with wide-field camera 3 to date. And the way that we don't saturate the detector when we do this kind of observation is that we actually, so you get the spectrum of the star onto the detector, and then you scan, you basically move the telescope along this. You don't keep the star in one spot, you just move the telescope, so you scan the spectrum down. And I don't even have to show you what that looks like, because you can see it right here. Please don't be upset. What this is a leftover persistence on the detector from one of those scans. This is the star itself, so after they took the scanned spectrum, they basically went and took a direct image of the star, and that's what you see here. But because the star is so bright, you still have leftover electrons from the scan itself, which is kind of really bad if you're trying to do faint cosmology stuff afterwards. So you should make sure that this doesn't happen just before your observations if you're doing that. Sorry. If it makes you feel any better, in case you were feeling bad, this makes it really hard for us to analyze this data set, because we're actually entering a nonlinear regime. So even though we're scanning as fast as we can to spread the light and not saturate the detector, we're still kind of in a nonlinear regime, just barely with the counts. So it's difficult to read this data set. But that's okay. I'm just going to show you this. This is extremely preliminary, and with my new analysis so far, it doesn't even look like this anymore. So there's no take-home message from this, except that what you're looking at is possibly, definitely one of the first versions of the first spectrum of a super Earth. Sorry, the first emission spectrum of a super Earth. So we've done a lot of transmission spectroscopy of these small planets, but it's really hard to do emission spectroscopy because you need a good candidate. You need a hot candidate that has an atmosphere. And this is it, 55 Cancri E. It's bright, hopefully, probably has an atmosphere, and it's a small planet. And the planet is hot and the star is bright. So all of that plays in your favor. This is the previous, I was telling you the Spitzer wavelengths. This is the previous Spitzer eclipse, right? So for emission spectroscopy. And then I told you that I got some extra Spitzer data. And I find it based on just one eclipse so far. I bring it down here, which is still pretty consistent with what the one that was before. So this is good. Basically, in the Spitzer wavelengths, we are consistent with previous results, and we're trying to figure out what the eclipse is like down here. We may or may not be able to actually see any spectral features, because you see our error bars are still pretty large compared to the spectral features we expect to see. But one thing we will definitely be able to do is determine the temperature of the planet with higher confidence. This black line here is basically just a black body, so if you expect the planet to just emit like a black body, then based on the temperature measured in the Spitzer bandpass, you can kind of figure out where the black body would be, and you expect that the temperature measured in the wide-field camera 3 bandpass would be more or less consistent with that. If it's not, then we're looking at something interesting. You can see that, for example, if this eclipse here was a lot larger, if it was like at about this level, that would tell you that this is probably a carbon carbon monoxide or carbon dioxide dominant atmosphere, which would be really interesting in and of itself. We're not seeing that yet, even though, like I said, this is very preliminary. But either way, we'll be able to either find a carbon atmosphere or rule out a carbon atmosphere, which is more than anyone has been able to do for this planet. So this is really exciting, and with James Webb, more of this. It's gonna be really fun. But we don't have more planets like 55 Cancri right now. However, we have TESS that's supposed to launch next year, maybe in 2 years. We'll see. And TESS is expected to find thousands of super-Earths and small planets around bright stars specifically, unlike Kepler. So all of these will be able to get their masses measured, which is great. So we can really put better points on that mass radius diagram and understand the densities of these planets better. And also we can more easily look at them with HST and the James Webb Telescope, because their stars, again, are going to be much brighter than the stars of the Kepler planets. So we'll be able to do that with a variety of instruments. So I'm excited about James Webb, the large ground-based telescopes, and small, maybe not a very well-known satellite, the European satellite called Cheops. I can tell you more about that later if you want. And you may have heard recently about this Proxima Cen view, which is basically the closest Earth mass planet to us. Now, this planet doesn't transit, so all we know is its mass from the radial velocity signal. Didn't talk too much about radial velocity, but here it is again. So we know its mass and we know its period. So from that, we know that it's roughly in a habitable zone. So one thing you could do, even if the planet doesn't transit, you could still do phase curves. So remember the phase curves I showed you, where there's like a transit here, and then there's an eclipse here, and then it goes up and down again? Well, you can do that even if the planet doesn't transit. So you can still see different sides. If you see the brightly lit side of the planet as it goes around the star, you just won't see a transit or an eclipse if the orientation isn't quite right. So it turns out that with 60 days observations with James Webb, we would be able to say whether Proxima Cen b, which is basically our closest habitable Earth-like planet right now, has an atmosphere or not. If it has an atmosphere, then that says that it's ripe for more observations after that. If it doesn't have an atmosphere, it probably means that we shouldn't keep looking. Probably is not ready or not likely to have any life or be habitable. But to first order, we'll be able to see whether or not it has an atmosphere, assuming anyone gives anyone else that amount of time. But this is the kind of signals we're looking at. So looking at the atmospheres of habitable planets is basically within reach now. It's possible with James Webb, assuming someone writes a good enough proposal, and it would be possible with the large ground-based telescopes. Okay, so I'm basically done. I'm just going to quickly go over this and then leave it up, but the take-home message here is that small planets are really, really interesting. We don't have any in our solar system, but they're frequent around all the other stars that we know of, or most other stars. And we can learn about them with transmission and emission spectroscopy, but it's still really hard because signals are small and there are a lot of degeneracies that you have to deal with, even if you do get a good enough signal. You can try emission spectroscopy for some planets as well, but really what we need is just more planets. So we can really build up statistical samples, so we can say if anything we're concluding from all this, like, can you have a hot rocky planet that has an atmosphere? Are all of these planets cloudy? Does this depend on the properties of the whole star, or is it representative of all small planets? We'll be able to see that with more candidates from TESS and the K2 mission, which is flying now. So I'm really excited about that. Thanks a lot.
You talked a lot about the cloudiness of the planets, mostly in kind of a negative way. But I wonder, has anybody thought about using the polarization of the light to look for how the light reflects on the planet? If you look in certain polarizations, can you see absorption? Basically look for the glare out of the planet and see if there are lines in that.
Yeah, I think that's really hard to do right now with current spectrum, because you don't have polarimeters on every instrument. Like Hubble doesn't have one, at least not in this way, and I think doesn't have one at all. So it's a really hard signal to check. One thing you can do is, people are modeling the composition of these clouds and hazes, and it really seems like along the wavelengths, you shouldn't see it as much. You should be able to see through them a lot better. So James Webb will help with that, I think. At mid-infrared wavelengths, we should be able to see through a lot of these cloudy atmospheres. If we don't, then we have to review our models of cloud hazes. So there is hope. I'd say there's a lot of hope. I really just wanted to present a realistic image of, this is really challenging. But we're doing it. These are really, really far away stars and really, really small planets. And the clouds are not going to stop us. It's just one of the main challenges we're running with right now. But it used to be that the challenge was just seeing those transits, even just seeing a transit in the first place, not even thinking about getting spectroscopy. Okay, so now we got spectroscopy and we'll have new challenges. That's fine. Yeah.
So on your mass versus radius plot, I mean, Earth and Venus are nearly identical on there. Are there systems with multiple Earths or super Earths? And if so, are they similar?
Yes, there are many systems with multiple super Earths. In some cases, the densities are very different. Some will be very puffy, and some will be maybe not quite rocky, but it'll span that. It'll go from like water-rich maybe to hydrogen. These are just idealized compositions, but a wide range of densities. And there are also cases where they have pretty similar densities. But it's really hard to say because a lot of multiple systems we know are from Kepler. The nice thing about the multiple systems is that you can get the mass from transit timing variations. So when you have a multiple system, you can more easily get the mass of the planet for a Kepler planet than when you have a single system. But even so, there's not that many systems for which we have the precision to do that.
So when you look at for these transits around stars smaller than the sun, I mean, there's like activity and flaring and stuff like this. Are these any particularly terrible systematic sort of in the regime you're looking at?
Yeah.
I mean, this makes it worse presumably, but I mean, does it?
You mean just stellar activity?
Yeah, selectivity. Like, so for example, yeah. And give an idea like what's
for transits and spectroscopy, right? So actually, there is an important thing to get the kind of signal to noise that I've been showing in these plots for the spectra. You need to look at not just one transit, but a few of them, and then just co-add them to get that signal to noise. Now, if the star is doing funny things on the time scale of the time you spent between acquiring or observing the transits, then you should try to understand your star well enough so that you can correct for that. And actually, a lot of the time now, when people apply for HST time to retransmission and emission spectroscopy, they pretty much have to say that we're also going to monitor the star from the ground photometrically over basically the time span of observations. So that you can at least say, well, if it's not very active, then it might not have an effect to the level of your error bars. But if it is active, you may be able to correct for it, just because you know. And by activity, I really just mean spots. So you'll just see like these periodic variability in the photometry. If that has a really large amplitude, then you can determine at what point in the stellar cycle was the transit taken and correct for that when you combine all the transits together. So it's important to keep track of the star as well, yeah.
But it's just like the sample's so small right now that not much is known about the activity of the stars.
There's all kinds of, for example, Proxima Cen B shouldn't be very active, but it is. Well, so it's active, it has spots, it's very spotted, but shouldn't be very active with that for its spectral type and age. And I think in the UV it also is not hitting very strongly, so people are trying to understand why is it active in some wavelengths and not in others. It's mostly a problem for radio velocity, activity, because you can actually get your radio velocity signal at a given period and amplitude, and that can just be perfectly mimicked by stellar activity, so you have to be really, really careful. It's hard for a star to mimic a transit. It's more a question of when you try to understand that transit or try to do spectroscopy, you have to use what you know about the star to correct for very systematics. But you're not going to get a star mimicking the transit. If the star is very variable, then what you will get is it'll just be really hard to find the transit because it's on top of another trend in the light curve. So it's hard to detect.
For the spectra, though, it's essentially still systematic.
It can be, yeah. And when I showed the Rayleigh scattering slope earlier, So some groups have shown that you can, in some cases, mimic that Rayleigh scattering with just spots on the star.
Okay,
You can, so I know in this case, that's not it. We calculated and the effect of spots just based on what we do know a little bit about the star. The maximum effect of spots would be 1/6 of that slope, 1/6 of the amplitude of that slope, basically. So it may contribute, but it's not the cause of the whole thing. Yep.
I'm outside my area of expertise, so you can educate me maybe. I think a lot of stars are in binary systems, but I haven't heard a lot about binary systems with Kepler data. So I wonder if there's an effect of the companion star, if there's any systems, if that perturbs the orbits and changes your estimates of masses, or if we just never found any around binaries.
Well, so for masses, there are planets found around binaries. So not one star in the binary, but around both stars. Kepler has found a bunch of circumbinary planets, the Tatooine planets. Though I don't think we even have radio blast experience actually, because the stars are too faint. But sometimes when you do measure radio blasts, you'll get your periodic signal for the planet, or you hope it's the planet. And that will be in addition to a long-term slope, maybe. So you'll just get like a sinusoid, draw the laser, but instead of going like this, it's gonna go like this. You'll have an underlying trend. And a lot of the time that means that there's a massive companion somewhere far out that's in the system. But basically what I'm saying is, if you don't have a multi-planet system, you're not trying to solve the motions of too many planets, you can pick those things out. But yeah, if you have a multi-planet system and you've got like all the planets, you're basically gonna have like a sum of sinusoids that are offset in phase, and you have to make sure you fit that well and you're not degenerate. You can be degenerate. 2 planets in resonance, so basically the period of one will be the multiple of a period of the other one. In some cases, you can have that system be degenerate with a single planet in an eccentric orbit, for example. So there are things that you need to do too. Those are very specific cases, like most of the time you can distinguish between the two. It has to be just the right resonance or just the right eccentricity. And that'll be mostly the dynamics. If it transits, that, who cares? Well, the mass will be hard to get, yes. But if it transits, you don't really care about the dynamics so much. You can do spectroscopy.
All right, let's go again.